Hey there, awesome physics students. Let's talk about charging an RC circuit. So here I have an RC circuit here with a battery. The voltage of the battery is V0, and I have a switch here, and if I turn the switch on, that turns the current on, and so current will flow out of the battery through the resistor, and charge will begin accumulating on the capacitor. So you can see this arrangement of circuit elements is very different from the discharging case, or somewhat different. So what happens if I follow the voltage across the capacitor over time? So if I look at this voltage across the capacitor versus time. Well, when I first close the switch, charges are going to flow out of the battery, as I mentioned, and accumulate on the capacitor. And so the voltage of the capacitor is going to be very small in the beginning. As the instant I throw this, the current is going to rush through this capacitor, but no charge has yet accumulated. And remember, for a capacitor, V is equal to Q over C. If there's no charge on the capacitor yet, there's not going to be any voltage across the capacitor. So we start out at 0. But then over time, as the current continues to flow, more charge will be deposited on here. And so the voltage across this will increase. Now what happens though is that as charge accumulates, the charge that you're putting on there is repelling. You're throwing positive charges on this and negative charges on the other side. As you cram more positive charges on this plate, it's harder to get new positive charges to want to go on that plate because the positive charges are all repelling each other, right? And so what you see is that over time it gets harder and harder to get more charges crammed on there. And so over time, it takes more and more time to get an equal number of new charges to go on there. And eventually you just can't get any new charges to go on there. And so over a long period of time, eventually no more current will flow. And so the voltage across the battery will be the same as the voltage across the resistor. So this will be V0, and this will asymptotically approach V0, the voltage across the battery. How do I know that it asymptotically approaches the V0 of the battery? That implies that the voltage across this is 0, right? Because if I look at the voltage across the battery, that's going to be equal to the voltage drop across R plus the voltage drop across the capacitor, right? So what I'm saying here is that the voltage across the resistor over a long period of time will be 0. And how do I know that? Well, let's look at the current that flows as a function of time. So when I first turn this on, charge is very happy to go on this plate, right? And so the current is very large and positive. But over time, it's hard to convince new charges to go on there because those charges are repelling each other. And so the current decreases, right? The motivation for the charge to flow becomes less and less. And over time, after a long time, it's really, really hard to get any new charges to go on there. And so it takes a long time to get any charge to move. If the rate at which the charges are flowing is very small, that is the current. So the current decreases over time. And eventually you cannot get any new charges to go, and the current will be 0, right? So the current asymptotically approaches 0 over time. So this one is what tells me what happens with the voltage across the resistor. Because the voltage across the resistor is going to be the current that's in the circuit times the resistance, if this decreases exponentially, this is going to decrease exponentially too. So it's going to be shaped exactly like this. So this is the voltage across the resistor. It's going to be shaped exactly like that. And in fact, it's going to start out at V0. How do I know it starts out at V0? Well, V0 is the voltage across the resistor plus the voltage across the capacitor. The capacitor starts out at V0 equals 0, or V equals 0, excuse me. So this one plus this one has to equal V0. And over a long period of time, V0 goes, or the voltage across the resistor goes to 0. So this becomes 0. But the total V across the resistor plus the capacitor has to equal V0. And so that means this one must approach V0 at a long time. Okay? All right, hopefully this helps you understand how the resistor, the capacitor, and the current and the voltage across the resistor vary with function as a function of time. And you can look up these functional forms in a book, but it's good to get some intuition about how why they're shaped the way they are.